Hop. So, goedemorgen iedereen. Het is een genoegen en een grote eer om met u hier te zijn. And that's as far as I will go in Dutch. So this, my claim to be talking about this topic is a short book that I prepared with a colleague at Cambridge University. And the theme for the day is about flexibility in design. And it is a new approach, I would argue. Not that we haven't thought about it before, but in the world of engineering and infrastructure design, I would suggest that it's relatively new. And it has the following features I'd like to talk about a bit with you, to have a discussion with you afterwards too. First of all, I think it's desirable. It's desirable because it recognizes uncertainty. Now, you would say that we've always recognized the various uncertainties that exist, but in practice, we have tended to look at the future and decide what it is required and take that as a definite objective, rather than recognizing our ignorance. It is practical. It is not particularly difficult to implement, at least not considering the other technical difficulties that we have. It is not something that, in a certain sense, we practice all the time in our daily lives. And it's valuable. This is the important point from my perspective, because to me, engineering is about producing good value for the resources you have. That is about being economical and useful with them rather than spendthrift, and using a flexible approach, case after case demonstrate that you can get much greater value overall than without it. And so, in general, when we are concerned, as we must be, and you in particular in the Netherlands have to be concerned about climate change, for example, and rising levels of the water, we have to be concerned about future-proofing our system, that flexibility is an economical way to do it. And in this connection, as I mentioned, I'm very happy to have the opportunity to learn from the great experience of the Rijkswaterstaat and to indirectly to be working with them. It's a great pleasure. So the outline for this morning, my little talk, is first of all, I'd like to define what I mean by flexibility in design, what it is and what is the elements of the approach. I'd like to talk about in some detail the elements that I think are crucial for it, that is realistic about the issues rather than, as I will suggest, that this standard engineering approach is not very realistic, that it is practical and valuable, and we're talking here that we can achieve things like 20 to 30% increases in expected value. This is an important one because in engineering we often fight for a 5 or 10% increase of efficiency, and with a flexible approach we can, and if we do it right, have really much greater achievements in expected value. And so it's an economical approach. So what is it? In general, flexibility is the capability easily to change either the capacity or the function of a system. So, of course, we can always change systems, but very often it's very difficult to do. So what it means to be flexible is that somehow we have done something in advance to think about how we're going to evolve if certain things happen. And they can be in either two ways. What we could talk about is in the system or on the system. In the system is part of a technical design. So, for example, in your laptops, you have USB ports. USB ports give you the capability, but not the necessity, of adding all kinds of features, some of which you already know about, and other things which have yet to be invented, perhaps, but you can plug various things in it. And, for example, you might want to have, you're going on a long trip and you might not be able to recharge very well, so you might like to have extra battery capacity. So you could have bought it originally in your computer, which would have made it much more expensive. Or you could say, well, thanks to that capability, the USB port, I have the capability to have this extra memory if I ever need it. I don't have to buy it right away. I can buy it later, or I might not ever need it. And that is flexibility in the system. I've done something technical to allow me easily to change the capacity or the function if I added a printer or something later on. Alternatively, or complementarily perhaps, the flexibility can on the system. That is to think, well, I could have a flexible time to implement it. I could think about building something now or in 10 years. I can keep that open depending on when I need it. When I need it, I will do it. And so one can think about it not just in terms of technological action, but in the timing action and the planning action. And it's also known in the literature as real options. I don't use it very much in terms of options because the field, subject of a Nobel Prize winning work in finance, involves a lot of assumptions and procedures which aren't really appropriate to engineering, but for those of you who think about it, it's a combination, an application, if you wish, of real options. So here's an example of flexibility in design. So this building that you see on the left-hand side, the short, stubby one in the middle, is the Healthcare Services Corporation building in Chicago. It was built about 25 years ago. It was a 30-story building with the capability to expand to another 27 stories, basically to double in height. The columns were built larger, the heating and ventilation systems were built larger, and various other features were incorporated so that it had the capability, if ever needed, that it could expand, double its size in essence. And this was done, it's now been completed for about 2 or 3 years. And so the building was designed with that capability. Now you could say, well, if I look at that building originally, I had all that extra stuff in it and I didn't need it. But it gave the insurance for the owners that they could expand if they ever did need it. But they didn't know. They didn't know if they wanted to double the size. And it saved, compared to building something larger, to have the extra capacity available. In other words, they deferred the cost for about 15 years. And that deferral at the cost of money that they had was like having it at 1/3 the price when they actually built it. So it was a very effective approach. So why would I say that flexibility in design is desirable? And the simple answer is because we have great uncertainty. We must recognize we have great uncertainty about what we need. We simply cannot predict the future over the next 50 years or 25 years. The life of any infrastructure is that long at least. And over those periods, there are too many trend breakers, surprises, and things that happen. The idea that it's within our capability to define what we need over the lifetime of a project is arrogant, and it is not realistic. So we need the capability to provide for real needs, not to think about designing for what we imagine might happen, and that was based upon some kind of having something that we imagined wrongly based upon incomplete information about the world years ago. So just think about the issues we're worrying about as nations, as communities, in terms of power and energy and water levels that 30, 50 years ago we hadn't really even known about, we hadn't thought about. There was a time, you may remember, that in the Netherlands it was believed that we should sell all the gas quickly because nuclear power, as I understand it, was the future. That's within living memory. But it's certainly different now, isn't it? So just think about it. This is the essence. We must recognize our fundamental inability to predict what we will need, and therefore we must, in recognizing that modesty, we must think about we don't know what we need to design. Ultimately, we have to provide something to prepare for it. Now, this is contrary to established practice. That is, Established practice is embodied in this diagram, which I won't explain in detail, but simply to point out that this is the traditional systems engineering V, designing how you do systems engineering, textbook material. Up in the upper left-hand corner for everybody, it says user needs. Step 1, determine the requirements. Define now what you are going to need over the next 30, 40, 50 years. Then, of course, if you know exactly what you need, then you can design all the bits and pieces and the components and the subsystems. But there's no way we can have a satisfactory answer to what the requirements are for 50 years. We can think about ranges, we can think about possibilities, but to define it as define the user needs, requirements definitions, that's not possible. So I would like to draw, first of all, the idea that we need to change the paradigm. Secondly, I want to suggest to you that flexibility in design is very possible. There are lots of examples. Some of them are the suspension bridges. The 25 April Bridge across the Tagus in Lisbon is one example. The George Washington Bridge is another. Each of those facilities was built with one level, and then a generation later on basically had another level built onto it because it had been pre-planned about that possibility if ever it were needed. Skyscrapers, I've shown you an example of them. There are plenty I could discuss. There are plenty more. Flood control works. I'd like to show you an image of Sacramento. Here you will recognize this kind of thing, or at least the American version of it. They're having a base that they're putting on that's going to be buried, and they're having a wall. Now, what you can do to be flexible about it is you can build the base to sustain a higher wall, but decide only to build a shorter bit of the wall right now and save yourself 1 meter or 2 meters of design and concrete and energy and effort, so you can build it so that you can have a higher wall if needed, but meanwhile you don't implement it all because you can save yourself over many hundreds of kilometers or so. You can save yourself on the height of the wall, so you have a flexible design where you can expand if necessary, but don't do it right now. So the flexibility also has value. Case after case shows great increases. What's the intuition? What's the magic of this? Well, first of all, it mitigates, it lessens the downside risk. Downside risk is that you may spend too much and you waste the money. So if I never needed the extra meter of the flood wall, for example, if I'd spent that, I would have wasted a lot of money. So not putting it in originally saves money. It reduces the downside, the possibility that you've wasted money. It opens opportunity on the upside. That is, you can add on to it the way you might want. So you can take advantage of that. You can, in the meantime, just as your computer with the USB port that you can add on to if you want, it lowers your initial capital expenditures. So you have these advantages of less downside risk, more upside opportunity, and at lower cost. This is a wonderful combination. More value, lower cost, benefit-cost ratio much higher. So it is clearly, when done right, with the right kind of design, it is a win-win approach. So let me just give you this as an example. This is from a deep water oil platform for a major company. This is from BP, as you can see on this particular photo of it. So we're talking about a deep water platform. The design team I was working with had used the most likely values for designing it, the most likely values in the price of oil and gas and on the quantity of oil, and designed it. They had a single best design. Now, of course, we know that the price of oil varies all over by a factor of 3 or 4 over the last 15 years, and the amount of oil that you can economically recover depends upon the price, but also depends on micro details of the field, where you can have the pressure and how you maintain the flow. So huge uncertainties. Now, let me show you this graph here. It's on the horizontal axis. The x-axis is the value. And we've taken off the numbers, but what you can, so not to reveal the source, but it goes from 0 to minus 100, but these are in billions of dollars in that kind of range. And on the other one, it goes in the positive direction. And on the vertical line is the probability. So it goes from the lower edge, which shows that there's no chance of it going below this amount for this particular design represented by this curve, to the maximum of about this amount. And this represents basically the cumulative distribution, what we sometimes call the target curve. So we have different designs. The original design of a very large platform was strategies 1 and 2, which basically had the possibility of substantial loss, a good probability of a gain, could be very large. On average, it was around here. What we helped them work through was a improved design that was flexible. So it principally had to do with building it smaller in the beginning. So you had modules that you would add on, 1, 2, 3, 4. So you had less chance of loss. If you put less into it, you bet less, you could lose less. So in this case, the loss seemed to be entirely eliminated by going from here to here. You had maximum value higher, because if you build it in modules, you could go to 1/3, 2/3, 3/3, 4/3. You could have a greater capacity. And overall, the expected value was 78%, because there was so much chance of loss here. But it's a substantial increase, which is the point. That is, you could have, by thinking cleverly about, in this case, in modules, but also about subsea connections, there are more details to it, but having a flexible design, lower the downside, increase the upside, overall greater value, and less cost at the beginning, exactly when things are less known and more uncertain and more risky. So looking back, what I'd like to leave you with, before looking ahead a moment, is that flexibility in infrastructure is desirable because it's a realistic view of it. And some people will say, well, that makes life difficult for the public to understand because it's not this, it's not that, it's uncertain. But actually, I'm very much a believer that the public is very intelligent and has a lot of common sense, because they know that in all their life, they raise their children. They don't know what the future of their children is going to be. They don't know whether they're going to be musicians or engineers or doctors or plumbers. So they understand that life is not fully predictable. Secondly, it's possible. And thirdly, it's valuable. So what I'd like to then look forward to for a few moments to finish is that overall, this is a way we should think about future-proofing our infrastructure responses to the future. So the essential issue, we need to recognize that our infrastructure lasts a long time, and we cannot know what our needs will be in advance. It's simply not possible. We're not knowing about them. We can think about the range, but we do not know. Life is full of surprises. We could list them if we want. You all know them from your own experience. Just think about the way fracking, for example, has completely changed the political and picture in terms of oil. The United States is the new Saudi Arabia in that respect only, thank goodness. The forecast is always wrong that what happened. What actually occurs is generally different greatly from what was forecast a long time ago. Just go back and think about the forecasts that were made 50 years, 30 years ago and compare with what's happening. They didn't get it. Even when the numbers look comparable, things have really changed. So It is true, for example, Schiphol, that the numbers of movements and passengers increased, but the whole way aviation is working, and what is KLM now as compared to what it used to be before, and what is happening compared to the competition with Ryanair's and other companies like that, it's all very different. The point is, we do not really know what the future is our infrastructure will serve. So how do we proceed in this basis? Spend just a moment here of how you think about what do we do in this context? We don't know what we're doing. Does that stop us? What do we do? Well, an obvious answer is, well, we'll make it strong enough, raise the dikes by so many meters, for example, to meet all future needs. That would be the wrong response. If we build it large enough, strong enough, high enough, etc., we will be able to future-proof it. But by definition, this would guarantee the future. If, of course, we could actually imagine what all the possible futures would be. But this overbuilding is expensive and wasteful. It's clearly expensive, but it's wasteful because if you focus on the extremes, you admit logically that you have over-designed for all, you've provided things that you might never need. So in that sense, it's wasteful. The problem is you don't know which ones you won't need, but there's a lot of things you will have done that you will not have needed, and it will be wasteful. Secondly, if you can defer the expense until later on, it is cheaper. You save the interest on it, or you save the discount rate. It's cheaper to do it later on in terms of present values. So it's better to build later when you know more about what the future is going to be, when you have more knowledge. So this is why I would recommend to you the flexible design, because it's a more efficient, economical way to prepare for the unknown future. Properly defined, it enables appropriate response to several possible futures. I've done things now, so if I need to go left, I can go left. If I need to go right, I can go right. Or I need to do anything, so I don't do it. So my computer, your computer with a USB port, you can add a printer to it, you can add more memory, or you can do nothing. So, and it defers some, flexible design defers investments, avoids some, and what you end up doing is it's lower cost per project because you don't do everything you might need right now, and it permits you, because you only have so many resources in any community, it permits you to do more projects faster and to serve more people. So the overall suggestion is that collectively we should spend less effort in trying to predict long-term future, which is in any case, it's unknowable, it's a waste of time to spend too much effort on it. Less effort on building the infrastructure that will meet some guessed-at future. We should call it not predictions, we call it guessing. And the emphasis on implementation of facilities that could, by extension or adaptation, meet several futures that might occur. So thus, you reduce immediate project costs and facilitate more projects and more service to the community. That's where I leave it. Thank you very much. You're a wonderful audience. I appreciate your listening to me in English. Actually, not English, I'm sorry, an American. Thank you very much.
Right.